For this problem, we're actually going to use all four proof methods shown on this page here. Right at the end, we're going to have a goal of the form there exists x such that p of x, and we're going to arrive at that by showing that p of a is true for some particular a. But instead of sort of re-expressing the goal that way, we're just going to have p of a appearing as a given. Okay, and then that will allow us to conclude this. So you can be on the lookout for that. All right, suppose f and g are families of sets. Prove that if f is a subset of g, then the union of f is a subset of the union of g. Let's try and sketch this somehow. So f is a family of sets. Let's suppose there are maybe just a couple sets in that family. And f is a subset of g, so that means g is also a family of sets. So g would have to contain those two sets and maybe some more as well. Okay, maybe we'll just put one more set in g. Okay, so f has these two elements, and g has these three elements. All right, so we have our antecedent here, and then the consequent. The union of f is a subset of the union of g. Okay. Well, the union of f is just the set of all elements of these two sets that are in f. Okay. Whereas the union of g would contain all of those elements and maybe some more as well, right? Whatever elements are in this last set down here. Okay. So it's pretty clear that the union of f, namely all these elements here, are all contained in the union of g as well. All right, so that's what we want to prove, and we're going to be using a letter like capital A for a set like this, and a little x for a point. Okay, for an element of one of these sets. So how does this work out? So there's our given, and our goal is a conditional statement. And so we can begin by aiming for a direct proof, moving our antecedent over, giving us a new goal. And then we have two subset statements here. So let's see, we could begin by writing out the definition of what it means for union of f to be a subset of union of g. And similarly for f being a subset of g. And now we have some universal quantifiers. And so let's begin with the goal. And we can just let x be arbitrary, which allows us to drop that quantifier. And then it's tempting to want to drop this quantifier as well, but remember, a is a set, right? It's not an element like x, and so we don't have an a yet. There is no sort of particular value of a for which we can take this statement to be true. Okay, so we need to hold on to that for the moment. And let's work with the goal some more. That's a conditional, so we do another direct proof. Bring x in union of f over as a given. And then what does it mean that x is in union of f? Okay, well that's the definition, right? There exists some set A such that A is an f and x is an a. Right? Remember, if you have your f here, which maybe has several, I had two before, I grew another one, several sets in it, then for x to be in the union of the sets in f, and the union of f means that it's contained in one of these sets. It's an element of one of these sets, which is itself contained in f. Okay. All right. And now we have an existential and a universal quantifier here with the same variable now with an a, so that's good. So existential instantiation gives us an a naught for which this statement is true, and then universal instantiation, we can take the particular case of that statement for a naught, okay, when a is a naught. And then we've got a modus ponens sitting there, right? Using the a naught in f together with the conditional, we get that a naught is in g. And we have our other unused given. We'll bring that down. And okay, let's go back and see what do we need to prove again. I'm trying to prove that X is in the union, and the definition of that, just like over here, is that there exists some A such that A is in this family G and X is in that set A. Okay. And we pretty much have exactly that, right? Maybe we can just take these and put an and between them so it looks the same, and bring down the same goal, and this is exactly what we need. We have found an A naught such that this statement is true, so there does exist an A. Okay. So that gives us our goal. Now let's write it up. The first step was to do direct proof. So we bring over the antecedent to make the consequent our new goal. So we can say, suppose F is a subset of G. We show that the union of F is a subset of the union of G. Okay. And then this had a definition like this, and we let X be arbitrary so that we could drop the universal quantifier. And we arrive here. Okay, and then the next thing after that was we did a direct proof, and we brought this antecedent over as a given. Okay, which left us with X in union of G as a goal. So we can combine those into a single line. Right? Let X be, well, instead of saying that it's completely arbitrary, let's say that it's an arbitrary element of the union of F. The reason I like to combine those is if I were to first say let X be arbitrary and then immediately afterwards say suppose that it's in the union of F, that's a little bit weird, right? It's not actually not completely arbitrary. So it's nice to combine those. It's a little bit clearer, I think. Okay, and then our goal is we show that, that X is in the union of G. All right, so how did we get that? Well, the definition of the union gave us that, well, gave us this existential statement, and then existential instantiation gave us an A naught. So we should introduce that new variable because X is in the union of F. There exists some A naught such that A naught is in F and X is in A naught. And that's just the definition of union. All right. And then we needed to get here, and that came from this statement, which way back when was the subset statement, right? So that got us here, and then universal instantiation got us here. And the purpose of writing that down was to combine it with A naught and F via modus ponens to get that A naught is in G. So let's say because A naught is in F, and then this came all the way from up here, and F is a subset of G. It follows that A naught is a subset of G as well. There is an element of G, pardon me. And that's by the definition of subset together with, well, universal instantiation, which I will leave out, and modus ponens. And finally, we just took the fact that these were both true, put an and between them. That gave us the definition of our goal, X being in the union of G. So we can write because A naught is in G from right here, and X is in A naught from up here, right? It follows that X is in the union of G. And that's by the definition of union once again. And that finishes our proof.